So let us now discuss in detail about the diamagnetic materials. This is a property of all materials in response to an applied magnetic field, and hence there is no requirement for the atom to have net magnetic moments. This is a weak negative magnetic effect who has a susceptibility of the order of 10 to the power minus 5 and hence may be masked by the presence of stronger effects like ferromagnetism, even though it is still present. The diamagnetic effect is based on Lenz's law applied at the atomic scale. Lenz's law states that change in magnetic field will induce a current in a loop of electrical conductor, which will tend to oppose the applied magnetic field. As the electron velocity is a function of the energy of the electronic state, the diamagnetic susceptibility is essentially independent of temperature. A diamagnet tends to exclude lines of force from the material. A superconductor is a perfect diamagnet under some conditions and it excludes all magnetic lines of force. Closed shell electronic configuration leads to a net zero magnetic moment. The spin and orbital movements are oriented to cancel out each other. Monoatomic noble gases such as helium, neon, argon, krypton, etc. are diamagnetic. In polyatomic gases like hydrogen, nitrogen, the formation of the molecule leads to a closed electronic shell configuration, which makes these gases diamagnetic. The other examples are sodium chloride, magnesium chloride, carbon diamond, carbon atoms, germanium, silicon materials also lead to a closed shell configuration, thus making them diamagnetic as the predominant magnetic effect. Most organic compounds are also diamagnetic. The paramagnetic materials, there are two distinct types of paramagnetism. The one that arises when the atom or molecule has a net magnetic moment, and the other one comes from the band structure or polyspin or weak spin paramagnetism. If the net magnetic moment within the atom or molecule do not cancel out, then the material is paramagnetic. Oxygen, for example, has a net magnetic moment mu of the order of 2.85 Bohr magnetron per molecule. Even if there are many electrons in the atom, most of the moments cancel out, leaving a resultant of a few Bohr magnetrons. In the absence of an external field, these magnetic moments point in random directions and the magnetization of the specimen is zero. When a field is applied, two factors comes into picture: the aligning force of the magnetic field and the disordering tendency of temperature. The combined effect of these two factors is that only partial alignment of the magnetic moments is possible and the susceptibility of paramagnetic materials has a small value. For example, oxygen has a susceptibility of the order of magnetic susceptibility of the order of 1.36 into 10 to the power minus 6 at 20 degrees Celsius. Any magnetic alignment is always fighting against the disordering effect of temperature, while mass susceptibility is independent of temperature for a diamagnet. For a general paramagnet, it follows the Curie-Weiss law. The next category of materials are ferromagnetic materials. So ferromagnetism, antiferromagnetism, and ferrimagnetism involve no new types of magnetic moments, but involve the way the magnetic moments are coupled. So when we see the ferromagnetic materials, all the magnetic moments are aligned in the same direction, whereas in the antiferromagnetic moments, the up and down magnetic moments are oriented in opposite directions. The moments are oriented in opposite directions, leading to the net magnetization zero. Whereas in the ferrimagnetic materials, the magnetic moments in the up direction have a higher magnitude as compared to the magnetic moments in the lower magnetic moment. So there they will have a small net magnetic moment. the two important ways of understanding ferromagnetism in metals are assuming that the movements are localized to atoms or using the band structure of metals. In metals, for example, iron, most of the electrons behave as if they are localized, and the number of attendant electrons could be a small number. In iron, there are 8 valence electrons which occupy 3D and 4s or bands. So out of these 8 electrons, only 0.95 in the 4s bands are free or attendant, and the remaining are occupy the localized 3D bands. Whereas in nickel, the corresponding quantity for the 3D and 4s is 10. So the free in the 4s will be 0.6, whereas the localized will have 9.4 in the 3D shell. Now let us start discussing about the magnetization dynamics. So in the steady state, you can see that when we apply any external magnetic field, we are not changing with time. The magnetic field or the magnetic movements or magnetization will orient itself in the direction of the magnetic field. So we can understand the magnetization dynamics by using the Landau-Lipps-Gilbert equation, which is given here. So for understanding all this equilibrium state, the excited state, and the dynamic motion, the Landau and Lipps gives the first term, and it tells about the rate of change of the magnetization with time. Then the Gilbert improved this quantity or this equation by introducing another term, which is the damping term, and that is why this equation is known as Landau-Lipps-Gilbert equation. So it states that the total rate, so basically when we talk about the LLG equation, it is the fundamental equation in the field of magnetism that describes the dynamics of magnetization in the magnetic materials. This equation combines the classical mechanics and the quantum mechanics to provide insights into the behavior of magnetic systems. It states that the total rate of change of the magnetic moment, the left-hand side of the equation, the rate of change of the magnetization, is fully controlled by the total torque acting on it. That is the right-hand side of the equation. The right-hand side of the equation consists of two main parts. One is the conservative torque, the first term, and another one is the dissipative torque, the second term. The conservative torque arises from the interaction between the magnetization and a conservative field, such as an external magnetic field. It aligns the magnetization with the field and is responsible for the precession of the magnetic moment around the effective field. So you can see here, this is the conservative. In the excited state, the conservative torque comes into picture, and it tends to precess the magnetization along the field, across the magnetic field. On the other hand, the dissipative torque, the next term, accounts for the energy dissipation and represents the effect of damping in the system. It introduces a damping parameter, alpha, also known as Gilbert damping constant, which characteristics the rate at which the energy is lost as the magnetization revolves around time. This dissipative torque ensures that the magnetization eventually reaches to its stable state. So this magnetization will not keep on continuously revolving around or precessing around the magnetic field or the effective field, but due to the damping present in the system, the magnetization precession will land up onto its equilibrium state after some time. So this damping will account that factor, and it is the dissipative force, where gamma is the gyromagnetic ratio, and it is a value of around 17.6 gigahertz per kilorastal. So Gilbert damping constant is the most important parameter which is obtained from the ferromagnetic resonance measurements, which we will discuss, which describes the microwave and spintronic functionality of the material of the ferromagnetic material. And the resonance, which we will see ahead, resonance occurs when HRF matches with the precision. The magnetization dynamics has a wide range of applications in the areas such as spintronics, magnetic recording, and magnetic resonance imaging. The figure represents the magnetization dynamics of a magnetic movement immersed in a constant magnetic field along the Z direction. So you can see that this shows the conservative torque. So the magnetization will process continuously along the external magnetic field. So this precession will be continuous. So the first term is the conservative, but due to the damping present in the system, so you can see that when the damping is present, the precession will not be continuous and it will land up to its equilibrium state when we have a damping. So depending upon the value of this damping constant alpha, so the precession will be more or small. So if it is of the order of, say, the damping constant will be more, it will quickly come to its equilibrium state. And if this damping constant will be smaller, so it will take more time to come, the relaxation time to come to its equilibrium position will increase. Okay. So the next slide explains the magnet and various applications of these magnetic materials. And as I already said, that these materials have a wide range of applications, in such as magnetic thin films can be utilized as a source of drain and as a source and drain in spin FET, which can overcome the conventional semiconductor technology. So nowadays, the conventional semiconductor technology have been looked as an alternative by the spin FETs by depositing the ferromagnetic materials or half metals, hustler alloys as a source and drain, and there will be a channel which is a graphene sheet in between. So when we apply the voltage across the gate, so we will have so this will overcome the drawbacks of the conventional electronic devices. Then we have used such kind of materials in spintronics, for which the well-known scientists Albert Fert and Peter Grunberg have received the Nobel Prize in 2009. The microwave devices, as the frequency with which the magnetization process is of the order of gigahertz. So we can utilize these materials for the microwave devices. And they are much more advantageous, that if we apply an external RF magnetic field in a perpendicular direction to the external magnetic field, so the resonance will occur. That means the precision of the magnetization and the precision of the RF magnetic field will match at a larger frequency, and there the resonance will occur, and that frequency is of the order of gigahertz. So these devices can be used for utilizing in the microwave devices. Then we can also use these materials for mass storage applications, like MRAMs and STRAMs. Then there are various biomedical applications where these magnetic materials can be utilized, like we inject these magnetic materials as a source of as a source of heat materials. So magnetic hyperthermia uses such kind of things. What we basically do, we inject these materials at the cancerous site, so and heat up these materials. So these materials will cause the vibration. So and the heating will, it will basically do, it will kill the cancerous cells, and only the normal cells will alive and the other cancerous cells will be removed from the, or they can be removed using the magnet. With the help of the magnet, they can be removed from the body. So they have a wide range of applications in the biomedical applications also. Now let us start discussing about how we can synthesize these nanomaterials. So we have seen that there are various categories of these nanostructures. There are different magnetic materials which can be used for these nanostructures and what are their applications. But now let us understand how we can synthesize these nanomaterials. So there are two basic ways by which we can synthesize these nanomaterials. So as you can see in the image, one is the top-down approach and another one is the bottom-up approach. So the top-down means we are lending from the larger to the smaller, and the bottom-up says that we are lending from the smaller to the larger. So we are going in the opposite. So bottom-up approach, it seeks to have smaller components built up into more complex assemblies. So bottom-up approach uses the chemical properties of single molecules to cause single molecule components to self-organize or self-assemble into more some useful conformations or rely on positional assembly. Whereas the top-down approach, it seeks to create nanoscale devices by using larger externally controlled ones to direct their assembly. So the top-down approach often uses the traditional workshop or macrofabrication methods where externally controlled tools are used to cut, mill, and shape materials into the desired shape and order. Micro patterning techniques such as photolithography, inkjet printing belong to this category, belong to the top-down approach. So, we understand this, but how we can synthesize the one-dimensional nanostructures and what are the one-dimensional nanostructures? So one-dimensional nanostructures represent the smallest dimension structures that can efficiently enhance the transport electrical properties. As we have already seen, the one-dimensional nanostructures include nanowires, nanotubes, nanorods, multi-layered nanowires, etc. They often exhibit new and enhanced properties due to their low dimensionality and interwire interaction as compared to the bulk material. So their surface to volume ratio increases a lot, which is aspect ratio. So that increases a lot when we go to the nanoscale regions and one-dimensional materials. The tunable properties can be achieved with controlled growth by varying deposition parameters such as electrolyte concentration, pH, doping element, length, and diameter of the nanostructures. One-dimensional nanostructures can also exhibit critical device function and thus can be exploited as both the wiring and device element in future architectures for functional nanosystems. Magnetic nanostructures with very high coercivity are promising candidates for data storage and other applications. And we can synthesize these one-dimensional nanostructures using various techniques like spontaneous growth, using evaporation, condensation, dissolution, condensation, or vapor liquid solid growth. Then the other technique is template-based approach, which we will be going to discuss in detail. So electrochemical deposition, electrophoretic deposition, colloidal dispersion, electrospinning, and photolithography are the other category of techniques. So as we have seen in the previous slide, that template approach is one of the method of synthesizing one-dimensional nanostructure. So what is this template-based synthesis? So this method uses cylindrical porous templates as a mold to deposit nanostructures such as nanowires, nanotubes, nanorods, multi-layered nanowires, etc. The templates like anodic aluminum oxide, polycarbonate membrane, silicon template with different diameters are available, which can be used as a mold to deposit the metallic or ferromagnetic materials, nanowires, nanostructures in these templates. The desired metallic material is filled in the nanopores by electrochemical deposition method. Electrodeposition often requires a metal film on one side of the freestanding membrane to serve as a working electrode on which electrodeposition takes place. And after deposition, the template is dissolved away and freestanding nanowires are obtained. So this shows the schematic of the porous alumina template. So they have the cylindrical pores where we can deposit the ferromagnetic materials in that, and this shows the top view of that porous alumina template. So you can see the pore, they have the pores of around diameter around 200 nanometer. So when we deposit any material in this, we can get the one-dimensional nanostructures. And if we etch out this mold, we will have the standing one-dimensional nanostructures available with us. Now we can commercially purchase these porous materials or the membranes or templates, but we can also synthesize in our labs also. So the porous alumina templates can be synthesized using two-step anodization technique. So basically we use an aluminium sheet as the cathode and the platinum as the anode, and the electrolyte which is used to anodize the aluminium is oxalic acid. So we apply a specific potential to first anodize to create the pores in this. So you can see this will create the oxidation of the aluminium first, and then the pore initialization will start creating. And after this pore initialization, we'll use the second step, which will be used for pore development. So the pore development will be the second anodization step. This is the first anodization step. So depending upon the potential we are giving, we can vary. So first, in the first anodization step, the pores which we will get are not regularly arranged, or they will be in the random directions. But in the second anodization step, we control the potential in such a way that we can achieve the regular pores in the aluminum sheets. So oxide grows at the metal oxide and oxide electrolyte interfaces. Pores initiate at random positions by field-assisted dissolution at the oxide electrolyte interface. Ordering requires appropriate potentials and long anodization times. Ordering represents results from repulsion between the neighboring pores due to the mechanical stress at the metal oxide interface. So we will have this pores of the order of, say, 60 micron, 100 micron. So in the alumina template, we can achieve the length of the pores up to 50 to 60 micron. The next slide explains the electrodeposition technique, and this electrodeposition technique is useful from the point of view that it is a bottom-up approach. Very large scale substrate can be used to deposit nanomaterials. So we will have upscaling to large substrate area. It is a low deposition time. We don't require very huge temperatures to deposit the nanomaterials like in other techniques like sputtering, PLD, where we require very huge or high temperatures. So electrodeposition technique can work at the room temperature also. And most important, it is a low cost technique. So if by just using 2 electrodes, we can deposit the nanostructures or nanomaterials in these porous anodic alumina templates. So this shows the schematic of the electrochemical cell which is used for the deposition of one-dimensional nanostructures. As can be seen, this is the alumina template, porous alumina template. One side of this porous alumina template is coated with a gold layer so that it can serve as a cathode. So deposition can take place in this. So we have the electrolyte solution. So it can be, say, suppose nickel sulfate, cobalt sulfate, iron sulfate, copper sulfate. So whatever solution you want, we dissolve that specific solution in the DI water. We have the reference electrode, and we have the counter electrode as the platinum, or anode as the platinum. So what is this counter electrode? It serves as a source of electron. The reference electrode is basically used to maintain the potential between the counter electrode and the working electrode. So when we give a specific potential, by seeing the dissociation of the electrolyte, so that specific potential is being maintained by the reference electrode between the counter electrode and the working electrode. So you can visualize in this that it shows the cathode. This shows the anode. On the cathode, we have the template mounted. So when the deposition takes place, the nanowires start filling in the pores. These are the images of cyclic voltammetry and chronoamperometry, which are basically the part of electrodeposition. So whenever we use any electrolyte, we should know what is the potential at which it will dissociate so that the deposition can take place. If we will not apply the appropriate potential, deposition potential, the deposition will not take place in the at the working electrode or in the templates. So the cyclic voltammetry helps us to determine that specific potential. So the plot ABC shows us the reduction plot, whereas the plot DEF shows the oxidation plot. So reduction will do the reduction of that, and the oxidation will again oxidize to form the solution again, solution back. So we determine the deposition potential from the cyclic voltammetry. The chronoamperometry shows the time variation of deposition in the template as a function of current. So this is the current versus time plot. So what we can see, a pre-growth stage occurs when a sudden drop of current takes place once the potential is applied through the cell, during which nucleation starts at the pore bottom. So you can see that there is a sudden drop of current, and the nucleation starts at the pore bottom. Consequently, a slightly increased current is observed, at which the metal is growing in the pores. As the pores are filled, the current pores are filled, the current remains almost constant, but it decreases with a large gradient versus time. At the final step, hemispherical caps originating from each nanowire form a coherent planar layer that expanded to cover the whole surface of the template. So again, what we will see, the current will remain gradual, but there will be a sudden decrease in the current when the hemisphere starts, over deposition starts to take place. Then again, once the over deposition, these hemispheres will again form a thin film, then the current will become continuous again. So we can analyze the growth of the nanowires or nanostructures in the template by analyzing this chronoamperometry curve as well. So this image shows the morphological analysis of the structures designed by us. So we have successfully designed one-dimensional nanowires. So nickel nanowires can be seen. So you can see that the uniform nanowires have been deposited in the porous alumina templates. And when we etch out these porous alumina templates, so we can have the nanorods and we can have the bulk nanowires as well. So when we etch out the long length nanowires, they lie down on the surface of the film. Then we were successfully able to design these nickel nanotubes also. So you can see that depending upon the thickness of the nanotube, there will be a variation. So this has a smaller thickness, and if you see this, they have a much more thickness. So we are also able to synthesize multi-layer nanowires. So multi-layer nanowires have a specific applications in GMR devices. So we can control the ferromagnetic, then this is metallic, ferromagnetic, metallic. So we can control the thickness of the metallic layer, and depending upon the specific thickness, we can control the spintronic GMR properties or MR resistance also. This explains how we can deposit the nanotubes in the structures. For nanotube growth in AO, instead of a thick gold layer, a very thin layer of gold, which is of the order of 10 to the power minus 10, which is of the order of less than 30 nanometer, was puttered on one side of AO template, so as not to completely block bottom of the pore. So we have this porous AO template. So what we basically do, instead of completely covering the pores at the bottom backside with the gold layer, we deposit very thin layer of gold so that it covers only the periphery of the pores. It does not cover the whole pore diameter. So when we start depositing, what will happen? These periphery, the deposition will occur only at these peripheries, and we can have the nanotubes as a result. So you can see here that these nanotubes, this is a Y-shaped nanotube, and this is the, depending upon the thickness, we can change the thickness also. So nanotubes wall thickness depends upon backside gold layer, as when nickel ion moves to the pores of the template under the drive of electric field, nickel ion firstly reaches the conducting gold layer of the pore mouth and is deoxidized nickel atom, and thus forms a tubular structure. The wall thickness of nanotubes also depend upon other factors like current density. So we have to control various different parameters by which we can deposit different thicknesses of the nanotubes. The structural and magnetic properties of nickel nanowires are shown here. So this graph shows the XRD plots of different nanowires such as nickel, cobalt iron, boron, nickel iron. So depending upon the properties, their XRD planes, reflection planes will vary.